Today, we are diving into one of the most exciting and, let's be honest, most hyped fields in all of tech, quantum machine learning. It's this incredible idea that could totally revolutionize AI as we know it. But what happens when the rubber meets the road? Well, the reality is a lot more surprising and, frankly, a lot more interesting than the theory. Let's get into it.
So let's just start with the big one, the question that's driving all of this excitement. Could the strange, powerful, and downright weird rules of quantum mechanics actually rewrite the future of artificial intelligence? That's the core idea we're here to unpack.
First up, let's talk about the dream, right? The incredible promise. Because on paper, when you combine the raw power of quantum computing with the intelligence of machine learning, it looks like an absolute game changer. At its heart, quantum machine learning, or QML, is all about harnessing the fundamental weirdness of the universe. You know how regular computers use bits that are either a 0 or a 1? Simple. Well, quantum bits, qubits, can be both 0 and 1 at the exact same time. That's superposition. And then they can be linked together through entanglement, this spooky connection that just doesn't happen in our everyday world. QML tries to take all that quantum magic and apply it to machine learning.
And this is really the why. This is where all that hype comes from. That first bullet, exponential state space, means a handful of qubits can hold a mind-boggling amount of information. And because of that, you get quantum parallelism. It's like being able to test out millions of possible solutions to a problem all at the same time. For machine learning, that's the holy grail, right? You could potentially find patterns in data that are just completely invisible to even our best classical computers.
Okay, so that's the theory, and it sounds incredible, almost too good to be true. So what happens when we actually try to do something with it? Let's bring this way back down to Earth for a practical reality check.
We're going to look at a super simple task, nothing fancy. The goal is to get a computer to look at these tiny 16 by 16 pixel images and just decide, is it a plus sign or is it a minus sign? That's it. This is basically the hello world of image classification.
And here are the results. A standard classical neural network nails it. 100% accuracy in less than 2 seconds. Done. The quantum models? Well, they get really good accuracy, 98, 99%, but look at the time it took to train them. One took around 3 hours, the other took more than 13 hours.
Yeah. 2 seconds versus 13 hours. You are probably thinking, what is the point? And that is exactly the right question to be asking. Why on earth would anyone do this? To get that answer, we need to pop the hood and see what's actually going on inside today's quantum computers.
And that brings us to where we are right now. We're living in what's called the NISQ era. That stands for Noisy Intermediate Scale Quantum. And I want you to really focus on that first word, noisy. It is the key to this whole puzzle. So here's the thing you have to understand. This stuff isn't running on some perfect, all-powerful quantum computer. It's actually a team effort, a hybrid model. You have a quantum chip doing the really hard quantum-y part of the calculation, but it's being controlled and steered by a regular classical computer. And the name for this whole setup is a variational quantum algorithm, or VQA.
And this is a great way to picture it. Think of the quantum circuit as the engine. It's got all this raw power. But the classical computer, that's the driver. It holds the steering wheel. It runs the quantum engine, takes a look at the result, and then tweaks these little knobs, those are the theta parameters you see, and says, okay, let's try that again, but aim a little more to the left this time. It's this constant back and forth.
So this whole process is a loop. Step 1, you define your goal. Step 2, you run it on the quantum processor. Step 3, you measure the result, which forces the quantum weirdness to spit out a normal classical answer. And then step 4, the classical computer looks at that answer and says, not quite. Let's adjust the knobs and go again. You do this over and over and over, slowly inching your way closer to the right answer.
But this whole elegant loop runs into a massive problem. A roadblock that can stop the entire process dead in its tracks. It has a great name, the Barren Plateau. Imagine you're in a foggy, hilly landscape, and your goal is to find the lowest valley. Your only tool is to always walk downhill. On the left, that's easy. You can feel the slope, you know which way is down. But on the right, you've hit a barren plateau. The ground is almost perfectly flat in every direction. There is no down. You're completely lost, and your algorithm has no idea where to go next. So, it just stops. It's stuck. So, what causes this giant flat spot? Well, there are a couple of main culprits. One is just that noise from the environment we talked about. These quantum systems are so fragile, the slightest disturbance can throw off the whole calculation. And, weirdly enough, sometimes the cause is too much of that quantum magic, too much entanglement.
But get this, here's where it gets really strange. We just said noise is the bad guy, right? Well, it turns out that's not always true. Some research shows that a little bit of noise can actually be a good thing. It can kind of jiggle the algorithm just enough to knock it off a flat plateau and get it rolling downhill again. It's this super delicate balancing act between noise that kills your calculation and noise that saves it.
So yeah, the noisy now is challenging, to say the least. It's why we're seeing those 13-hour training times. But these limitations aren't a dead end. The entire field has its eyes on the prize, on the next great era, the fault-tolerant future.
And this is the main point. All that world-changing exponential speed-up stuff we dreamed about at the beginning, no one really expects that from today's noisy machines. That's the promise of future fault-tolerant quantum computers. Machines so advanced they can actually correct their own errors in real time, protecting the calculation from all that noise. And this right here, this is a little glimpse of that future. It's a famous algorithm called HHL, and it's designed to solve gigantic systems of equations, which is a core task in science and engineering. On paper, it offers a massive speedup, but to run it, you need the kind of perfect, error-corrected quantum computer that we just haven't built yet.
You know, there's this really cool cat-and-mouse game going on. Every time quantum researchers announce a new super-fast algorithm, the classical computer scientists get inspired and figure out new tricks to make classical algorithms better and close the gap. It's this awesome competition that forces everyone to really zero in on the problems where quantum computers will have a truly undeniable, unbeatable edge.
But there's another giant hurdle for the future, simply getting data into the computer. I mean, what good is a lightning-fast algorithm if it takes you 1 billion years just to load the problem? It completely cancels out your advantage. The big theoretical solution for this is something called quantum RAM, or QRAM.
And this visual gets the idea across perfectly. A normal computer has to fetch data one piece at a time. Get me item A. Now get me item B. The dream for QRAM is that it can use superposition to grab all the data it needs at once in a single step. It is a monumental engineering challenge, but without it, many of these amazing future algorithms just aren't practical. All right, so we've seen the mind-blowing promise, the kind of frustrating reality of today, and the huge challenges for the future. So what's the big takeaway? How should we really think about quantum machine learning? It's about a whole new paradigm for computing. And this is probably the most important thing to remember. QML is not going to replace the AI that classifies cat photos on your phone. Classical computers will still be way better and faster at tons of tasks. QML is a highly specialized tool, designed for problems that are either fundamentally quantum to begin with, or have a structure that just perfectly maps onto the way a quantum computer works.
So where will it be a total game changer? Analyzing data that's already quantum, for one. But the big one, the one that gets everyone excited, is simulating nature at the most fundamental level. Think about designing a new drug. A molecule is a quantum system. Trying to truly understand it with a classical computer is incredibly hard, but a quantum computer speaks its native language. That makes it the perfect tool for the job. And the same goes for discovering new materials or solving absurdly complex problems in finance and cryptography.
So let's just end with this thought. We are at the very, very beginning of this journey. It's like we're in the vacuum tube era of classical computing. But the ultimate promise of QML is to build machines that process information the way nature itself does. So the real question isn't whether it will replace what we have now. It's about what entirely new problems we'll be able to solve when we can finally compute at the scale of nature itself.